Class, and I want to say I'm so proud of how far you've come. All right, so in this particular course, we're going to be talking about video classification, just as we have in image classification. Let's not forget what we learned in our last class, which has to do with video processing. Just as we have image processing, we have video processing. All right, so in the last class, we learned the rudiments of what exactly is video processing, the difference between video processing and image processing, and how these are interlinked. All right, so this time around, we're going to be diving into video classification. And in this class, we're going to be working with some video data, and we're going to be training some of this data, running them through some pipeline, and then running some predictive model with respect to classifying whether this particular video is this or this particular video is that. All right. So I want you to listen attentively as I walk you through video classification in detail.
Hello, welcome back to class. So today we are going to be diving into introduction to video classification. So in the last video we talked about um, you know video processing. So in this video we're going to be talking about video classification. All right, so in this content we're going to be looking at what exactly is video classification all about. We're also going to look at sample video classification data sets. I'll be making reference to the HAVA data set. Then we're also going to look at the ActivityNet. It's ActivityNet, an introduction to Action. Alright, so what exactly is video classification all about? Just like we have in image classification, we also need to talk about video classification. So video classification in computer vision is the task of automatically assigning a label or a category to a video based on its content. This process involves analyzing the frames and images and the temporal relationship between them to classify a video into a predefined category. So let's just assume you want to be able to, let's say you have different videos of let's say videos of cats, videos of dogs. Do you understand? So when you pass in a video and then it's all cat that is there, then it can say, okay, this video can be classified as a video for cat, or this video can be classified as a video of dog. But it becomes difficult when you now start, it becomes pretty much more advanced when you now have different labels or different classes within the video. So you might want to look for a much more generic classification to give to that video. And then of course, as we advance in video processing, we're also going to look at multi-video classification or multi-object classification in videos. But let's talk about video classification primarily. So what are the key concepts in video classification? There are two things: temporal information and frame level feature that you need to be aware of. Number one, unlike traditional image classification, where each image is processed independently, video classification takes into account both spatial. So when we say spatial, we are talking about frame level, and temporal. Spatial basically means you are looking at just a single frame, and then temporal basically means you are talking about the across frames. So spatial, single frame, temporal, across the frame information. This allows for the recognition of dynamic patterns such as motion, sequences, and events, which are crucial for accurate classification. Then we also have frame level feature. So in video classification, when we talk about frame level feature, we're talking about each individual frame in a video can be treated as an image and analyzed using computer vision algorithm. However, the classification decision is not based solely on one frame, but the aggregate information from all frames. So sometimes you might want to take a particular frame, do your detection, do your prediction, then you now use the information you've gathered across the frame, right, to be able to make a decision with respect to what was embedded in the video. So quite a number of people do that a lot with respect to video classification and video processing. All right, let's keep going. So we also have other things you need to be aware of: temporal modeling, multimedia features. So for temporal modeling, we are literally talking about in video classification. When we talk about temporal, when we say spatial, we mean frame. When we say temporal, we are talking about the across frame to frame. So you can have like 50 frames, 100 frames in 1 second. So when we're talking about temporal modeling, we are talking about to capture temporal patterns and relationship between frames, such as movement or changes over time. So video classification often involves specialized model like recurrent neural networks, RNNs, or 3D convolutional neural network, which is CNNs. And of course, you know that convolution is very good at modeling frame level kind of data, and then you just have to have a spatial representation or a temporal modeling of it, and you can always use models like recurrent neural network or convolutional neural network, which you've been introduced to. You might also want to check out recurrent neural networks, which was not covered in this class, but you can also check out what it's all about. Then we also have multimodal features that you need to be aware of. Multimodal features basically implies video classification may also incorporate other modalities such as audio, text, subtitles, or metadata to provide more robust prediction. This particular common in tasks like action recognition in videos with spoken dialogue. So for instance, you want to be able to predict the action that was performed in a video due to the commentator's words. So that's what we are talking about when we say multimodal feature. So you can actually classify a video to be a sports video because it has some commentation, and the words looks like a football kind of words. Then we have maybe text information from a video, maybe subtitles. The video has some subtitles, so or it has some metadata or some extra information that can literally help with respect to the video classification alongside the frame level analysis or decoding. I want you to have an understanding that a 1 minute video, for instance, has 60 seconds, right? That's 1 minute. 60 seconds, imagine you have FPS to be equal to 30. So you're literally saying that one second is actually 30 frames. So literally in a 1 minute long video, you are literally talking about 60 times 30. That's literally 1,800 frames. So and that's 1,800 images. When we say frames, we're literally saying images or an array, which can be represented as an image. All right. So video classification is way different from image classification. It's another advanced level of computer vision that deals with how you interpolate images and interpolate frames. That is the spatial, which is the frame level, and temporal, the relationship between frame and the next frame and the next frame until the last frame. Okay. And that's what video classification is all about. So what are the processes involved in video classification? So we have pre-processing. So in pre-processing, we have frame extraction. And that was one of the things I was talking about in the last video when we were talking about sampling. So if you remember, when we wrote the code, we wrote for I in TQDM enumerate number of frames. Then we now did video cap.read. So ret, frame is equals to video cap.read. So when ret is true, that frame, you are literally trying to extract each frame. You are looping through the frame. So that's frame extraction. And you can basically say after every 10 frames, that's roughly what we call frame sampling or frame extraction. So extract frames from video at fixed intervals. So like 1 frame every second. So instead of 30 frames in 1 second, you might say, okay, after every 1 second, that is after every FPS, or after every 30 FPS, 1 frame, okay, or based on other heuristics. Then we also have other preprocessing like maybe resizing, normalization. Most times in video classification, you are not really talking about data augmentation because you have enough frames to deal with. You have enough frames, but sometimes there are stages whereby the video is of low quality, the frames are the FPS is of low quality, and you need to do some upsampling or augmentation, but people hardly talk about that when you're trying to analyze frames. Okay, unless you want to start doing video generation and you now want to train more videos and the likes. So resizing and normalization, that is, you resize the frame to a fixed size, normalize the pixel values, and also perform other typical image processing types. This basically what I've said is we've seen that, we've demonstrated that a lot with respect to frame based analytics. All right. Okay. So next on the list is feature extraction. So when we're talking about different types of processes involved in video classification, we talk about feature extraction. So what exactly are we doing when we talk about feature extraction? We are talking about, for each frame, features that are extracted using standard image-based technique like convolutional neural network for spatial feature extraction. Then we also have temporal features are captured using models like, so for the spatial, that is the frame, that's the spatial extraction or spatial processing. You can use convolutional neural network. And then for the temporal features, that is the relationship across all the frames, you are literally using what we call RNNs or LSTMs or 3D CNNs to understand how frames change over time. Okay, so that's what we mean by feature extraction. Next on the list is model training. What are the processes involved in video classification? Model training. Once you are done with pre-processing, then feature extraction, which is CNNs, temporal features, captures like RNNs and LSTMs, you want to talk about model training. Now, in the process of model training, what we are trying to do is you are training a deep learning model such as maybe a CNN to LSTM or a 3D CNN or a transformer. You are using it to learn from the spatio-temporal features of the video. So the model is trained on labeled video datasets, which each video is assigned a category or class, e.g. soccer game, person running, cooking, person dancing, this person is eating, so many features like that. Okay, so that's what we talk about the model training. So you can basically see that when you are talking about video classification, you are literally talking about a bigger version of not just CNN, not just LSTMs. What we've been doing in image processing is, CNN. But in this case, you can basically see that you can actually stack CNN models together, stack LSTM models together, stack 3D CNN models together, or stack a CNN and a transformer together, or you create a transformer model. Okay, then the next one after model training is classification. So after training, the model predicts the label for a new unseen video based on its learned features. In some cases, the classification can also involve multiple labels if the video falls under more than one category, e.g. sports and soccer. So in situations like sports or soccer, you can basically have somebody running and one person is dribbling and the other person is standing. One is intercepting while the other person is waiting for the ball to get himself or something, or is running, or is kicking, or is making a pass or a shoot. So several actions are happening at the same time. So but when you're talking about video classification, you can basically say, okay, this is that's a soccer video. But when you're not literally trying to talk more about what is actually happening in the soccer video, that's when we are talking about action recognition, and that will lead us to activity nets and some other networks that have been built over time, or that has performed so well over time with respect to video processing. So what are the types of video classification. Number one is action recognition, which is one of the things I just made mention of. Now, this involves identifying the action or activities that occur in a video. Example includes detecting actions like running, jumping, cooking. Okay, and it's used in areas like sport analytics, surveillance, security surveillance, and human computer interaction. Then we also have scene classification. This involves categorizing the overall scene or context of a video, such as classifying video as indoor, outdoor, beach, forest, you know, scene-based kind of classification. So that's another type of video classification, and it's applied in areas like video recommendation system or content tagging. So you can basically see video classification is something being used vastly amongst that is applicable to a lot of things that we do in our world today. Then we also have event detection. This type of is similar to action recognition, but this type of classification aims to detect specific events or occurrence within a video. For example, identify when a goal is scored in a soccer game or when a crime happens in a surveillance game. That's another crazy level of computer vision or another advanced level of but all these things are possible. You can actually solve problems like this. We also have video gen classification. Now this involves classifying videos into genres like comedy, drama, action, documentary. So there are different types of videos. That there are some videos when you watch them, you know this is a comedy video. There are some videos that you watch them, you know this is an action video, because they are taking out a lot of actions in it. There are some videos whereby when you watch them, you know this is a documentary of maybe reptiles or maybe cats or dogs or animals or something about animals, right? And this type of classification is widely used in video streaming platforms like YouTube and Netflix. So you can be a computer vision engineer that has learned computer vision so well that you are working with the likes of YouTube or Netflix in helping them improve their action classification algorithms or models to better serve people or to better create recommendation systems for them. So what are the different methods used in video classification? So let's quickly go through that. What are the different methods used in video classification? Number one, convolutional neural network. Very, very important. We've learned that. So traditional CNNs are excellent at extracting spatial features from each individual frame, but they do not capture the temporal relationship between frames. However, they can be used in combination with temporal models like RNNs to classify videos. We've seen that a lot. Okay, we've seen that a lot. Of course, that's why we said they can be used with temporal models like RNNs. So when we talk about temporals, we are looking at frame-to-frame interaction. Then we have 3D convolutional neural network, that's 3D CNNs. So unlike traditional 2D CNNs that we are very used to, that operates on individual frames, 3D CNN works on sequences of frames, that is video clips, by adding an extra dimension to the convolutional process. This allows the model to extract both spatial and temporal feature in a single network. So you can basically feed in a video, maybe a 1 second clip, into a 3D convolutional neural network to be able to make predictions or do some video classification or something. We might get there, try that. We should be able to demonstrate that. Okay. But it's just more or less like the same thing that we've done with respect to 2D, just like you have in image classification. So all you just have to do is to recreate the network, get your data loader, get your data set, get your data loader, then recreate the network. Then of course you have your augmentation processes and technique, such that once you are feeding in the network, so instead of let's say 224 by 224 by 3, you are literally passing in, let's say 50 by 224 by 224 by 3. That's 3 into the 3D convolution. All right, so that's what we're talking about here. Then we also have recurrent neural networks. These are the kind of models used in video classification. RNNs are their variants, that is LSTMs, are used to capture temporal dependencies between frames. So like we say, RNNs and LSTMs, they are used a lot when you are trying to, let's say you are trying to build a CNN model and you are using convolution. So you want to build a CNN LSTM system. So the CNN is actually learning on the spatial, that is the frame level, and then the LSTM is actually relating or connecting the features or the results from the frame level, or the details that was extracted from the frame level, and is interpolating it across frames in order for it to be able to make prediction with respect to what happened within the video or something. So these models are effective in recognizing patterns that span multiple frames, such as sequences of action. Then we also have the transformers, which is one of the generative models. We talked about GANs, but we didn't talk about GPTs, transformers, attention. These are things that you might want to check them out. So transformers, recent advancements have also seen that the use of transformer, that is a model architecture initially developed for natural language processing in video class, is now very, very applicable in video classification. Actually, transformers are used more in image classification and a lot of other things, but we've now seen that transformers are much more results, they generate better results even with in computer vision, CNNs and the likes. So these models can handle long range dependencies between frames and efficiently process video sequences. So what are the challenges that we need to be very aware of in video classification? I've spoken about that, a lot of frames you are dealing with. So number one, high dimensionality. Video contains large amount of data, and processing them efficiently while maintaining accuracy is a significant challenge. So each video can have hundreds or thousands of frames, leading to a very high dimensional data. I've once tried processing a soccer game, and of course it's a 90-minute game. 1 minute is so by the time I did the computation of the total frames I'm trying to process, which is a 90 minutes game, I'm literally processing roughly about let's say 200,000 frames. I think I've done as far as, for a 90 minutes game, I've done as far as 300,000 frames at once, and you have to process this within 1 hour. So that's massive amount of GPUs, massive amount of compute, and you have to be able to extract actions that happened across the frame. So that's literally object detection at work, object tracking at work, spatial, extraction of the datas, the people and the likes, with object detection and the likes, plus post estimation running behind, segmentation running on one end, just a lot of models running at the same time. And that's one of the things that makes AI systems quite robust, or computer vision systems very robust at identifying some of all these things or doing so high dimensionality, that is, there's so much data, and that's the reason why a lot of people hardly do augmentation or upsampling us, because you have enough data. Then we have contextual understanding. So understanding the context of a video requires considering both the spatial feature, that is the content of the individual frame, and the temporal feature, how the frames evolve over time, which can be very, very complex. And that's these are some of the challenges, or the that you should be very aware of when it comes to computer vision. So the more you advance in computer vision, there are very fewer people that solve problems like this. So these are some of the challenges. Then we also have challenges with respect to data labeling. So imagine you have a 90 minutes video and it has 200,000 frames. Labeling is quite difficult, right? Because you are dealing with thousands of frames, thousands of images, which is quite difficult. And that is why I introduced you to the sampling technique in the last video, even though I didn't demonstrate it, but I also want you to go check out how to implement sampling techniques. So Large labeled video datasets are needed for training deep learning models. Annotating datasets can be time consuming and expensive, especially for complex tasks like action recognition. So that's the reason why we now have companies like Dataloop and the likes that do a lot of data labeling, because you want to solve an action recognition problem, you need to do a massive amount of data labeling. There are also companies like Human in the Loop and so many other things like that, companies like that, Scale AI and the likes, that are actually solving this kind of problems that are quite very challenging in the computer vision ecosystem or the AI ecosystem at large. So real time, we also have challenges with respect to real-time processing. So for real-time application, e.g. surveillance or autonomous vehicles, computer vision is applicable in those areas. AR, VR, autonomous vehicles. Video classification models need to operate quickly with low latency. So when we say low latency, that is, we are basically saying that the system is computing the information as fast as it can in milliseconds. And when you're talking about surveillance, you are literally consuming, let's say, 30 frames in 1 second. So you need to be able to process, 30, 60, 100 frames in 1 second. So literally, you really want to make your model so efficient that the latency is extremely low and processing is in real time, which requires very highly optimized algorithms and hardware. So this is one of the reasons why people talk about GPUs, TPUs, because now you're processing large amount of data and computing them. So what are the different applications of video classification that you should be aware of as a computer vision person? Number one, video surveillance, like we said, identifying abnormal events, tracking individuals, or detecting specific actions like theft or violence. It's also applicable in sport analytics, analyzing player movements, actions, or game events like goal scoring and passing. Then it's also applicable in entertainment, that is categorizing video content on streaming platforms such as YouTube and Netflix. It's also applicable in autonomous vehicles, understanding and classifying objects and actions in video fields for driving decisions, such as pedestrian, other vehicles. Healthcare, analyzing medical videos for diagnostics purposes, such as detecting signs of diseases in radiology videos or analyzing surgical, events. Then it's also applicable in social media, categorizing video content for recommendation, ads, content moderation. So there are some AIs that have been built, optimized, low latency to be able to do all these things effectively. So literally computer vision. I want to talk about video classification dataset. So we have what we call the AVA dataset. But before I talk about the AVA dataset, let me bring this down a little bit. So AVA dataset. So AVA dataset is a video dataset on atomic visual recognition, and one of the reasons why I'm introducing you to this is because so it's a video dataset of spatial and temporal localized atomic visual actions. So I'm introducing you to this because we're now getting into the point of computer vision whereby writing code is not just it. Reading what people have done is more like it. So this paper, I like to read, and that's the reason why, as a computer vision person, as a researcher, or as an engineer, this applies. You need to be able to read some of all these papers, check out some of all these PDFs, be able to have an understanding of what was this data set all about, and what kind of problem was it solving. So dataset like AVA were one of the first set of data sets that people had to experiment on in order for us to have some pre-trained models with respect to video classification, which I would be trying out very shortly. But I just want you to take a look at some of these data sets. You can see left, sit, talk to, So the person on the left is sitting and is talking to and is watching. The person on the right is crouch and kneel, that is, he's trying to listen and also watch. So literally you can basically say he's trying to, like, spatial, spatial focus on the frame, right? And temporal, you are usually trying to see the relationship between what the person is doing, and you cannot know, the person is sitting down, talk to, watch, if you've not looked into the temporal relationship across the frames. Okay, so you might want to so this paper introduced a video data set of spatial, temporal, localized atomic visual action. The EVA dataset densely annotates 80 atomic visual actions in 430 15-minute video clips. So they are about 15 minutes videos. Each of those about 430 videos. Each of those videos are 15 minutes long, and across all these videos, this data set literally annotated about 80 different classes of actions, of things that people are doing. So this led to so you might want to read more about this data set. It was released in 2018. So there are a lot of other things that has been done since then. Okay, not just EVA data sets. There are a lot of other data sets like Kinetic 300 for Kinetic 400. That's data set of action recognition, looking at about 400 classes, 800 classes, 700 classes of action recognition, 800 classes that people have trained on. So there are a lot of data sets, just like you have ImageNet and image, you have ResNet that has been trained, and VGG pre-trained models. We also have pre-trained models for video classification data sets. All right, so let's go ahead and do some hands-on. And in this point of hands-on, I would love to introduce you to RunPod. So I visit RunPod. So when you visit runpod.io, just visit it, create an account, try and load it with some credits. I just had to load it with about, just for this experimentation, I had to quickly load it with about $20, just to demonstrate what we have here. Then you can basically see different pods. Basically it's a GPU providing platform. So we also have Lambda Labs. Lambda Labs is also another platform where you can have access to GPUs. It's an AI developer cloud platform where you can have access to GPUs of your choice. Now, one interesting thing about pods here is that you can actually deploy those pods. So they are in different costs, very cheap, right? So I want to use this A40 GPU. It's roughly about $0.44 per hour, and it has about 48 gigabyte of VRAMs and then 48 gigabyte of 9 vCPUs. All right. So there's A100 SMX NVIDIA. This is a previous generation type of NVIDIA GPUs. These are latest generation of NVIDIA GPUs. H100. There's RTX 4000, RTX 6000, and these are the costs. And of course, you can actually spin up as many GPUs. So there are GPUs that have about 282 VRAM, so you can actually view those ones. So you can basically see this one has 1004 gigabytes of RAM, and it's 104 vCPUs. Most of our CPUs, our laptops, is just 4 vCPUs. Some are 4, some are 8, some are 16 vCPUs, but this one is 104. This one has about 96 vCPUs, and this one has about 320 gigabytes of RAMs, and literally it costs roughly $12 per hour, and it has about 4 different. So that's GPU 0, GPU 1, GPU 2, GPU 3. So this one has about 6 when you spin them up, you basically see some of them. So there are quite a lot of so this one you can see H200 SMX. This is roughly about $30 per hour. You can actually access a lot of these GPUs, try them out. So let's spin up an A40. So to spin up an A40, luckily for RunPod, RunPod gives you GPU. It gives you kind of a Google Colab kind of interface. You can also SSH, and that's the reason why I'm recommending it, because it's like $0.4 per hour. So you can deploy on demand. So when you deploy your pod, you can actually access it remotely via URL. So just follow through with me. So while this is popping up, so you can actually deploy several pods. So click on run. You can connect to your pod. You can make some edits to your pod. Container disk. This is more or less like Docker, but I would love my container disk to maybe be 200, or set it to do a volume disk. You can set it to as no matter what value you want to set it to. You don't need anything to tamper with here except for this. You can leave it at 20 gigabytes or 20 gigabytes, but because we are dealing with video data, so it's going to download some data into the GPU that might be large, or so that's why I'm just putting it at 200. So another thing about RunPod is that it gives you access to so while it is recreating, so it allows you to know your GPU usage, your GPU utilization, pod utilization, and so many other things here. So basically the next thing is for us to connect. So you can see CPU 0%, GPU 0%. So basically the next is to connect. You can connect via Jupyter Lab, or you can SSH into the pod from your local, or you can connect via Jupyter Lab. So Google Colab gives us about 15 gigabytes, which they've tried so much, but I just want to expose you to some more GPU stuffs with RunPod. So you can see I can access it. So you can actually spin up kernels. You can spin up terminals. You can let me just so you can spin up terminal. You can spin up terminal, and then so you can spin up terminals. Alright, so you can spin up terminals, and if you do NVIDIA SMI, you basically see that okay, this is about 46. This is just a single GPU core, and it's about roughly about 46 gigabytes. So one of the things you need to first of all do is platforms like this. Of course, you can also create your own notebook. You can create a notebook, so you can do all your pip install, blah blah blah, pip3 install, Ultralytic. Let's just say something like that. But one thing about some of these GPUs is that they are kind of fresh. There's no Conda. There's no Anaconda. If you type Conda, for instance, it's going to say Conda not found. So there are quite a number of tricks that you might want to get familiar with, and this is one of the reasons why when you're dealing with GPUs like this, you might also want to learn some what they call it. You might also want to learn some Linux commands. So something like apt-get update. Definitely it's supposed to be up to date, but sometimes you might want to run that apt-get install ffmpeg, or let's say install cat nano and some other things like wget. So let's see. So let's see. Does it recognize wget? Okay, it recognized wget, so you can download files into the GPU. Apt-get install nano. So let's say you want to be able to write a file script, or okay, let me reload this page. Okay, there's a little issue with network here. Let's spin it up again. Alright, so now I can do nano dot. Let's say I want to create let's say train.py. So I'm just giving you, so you can actually edit, create files and all of those things. Train.py, so literally to create the file and some other things, so first and foremost, you want to set up Conda. So one of the things I want to introduce you to is Action. So I want to take one of their I also want you to go through some of their work here with respect to, so Action is literally, I want to go straight into action recognition. So Action is a package in Python. You can actually create, so but it's dependent, you need to install Conda. So these are guides. They have engine, CV is like OpenCV, detection is like detection, like object detection. Post is their mini library for post estimation. So these are guides on how to install the package. Then of course, if you want to train your own custom data, you have your own video data and you want to train it, you can follow their guides with respect to training the data. You can also follow their guides with respect to preparing a data. Okay, so this is guide on how to prepare a data set. Maybe you want to train a custom action recognition data set, skeleton based audio recognition, spatial temporal action recognition, temporal action localization. These are some of the things we're going to take a look at in the coming videos. But first and foremost, let me walk you through how to set up a GPU, your own GPU on Colab. So first and foremost, I need to sudo apt, or let me just say cd. Alright, so let's download the Anaconda. So sudo apt install ffmpeg, and also we want to install sudo, let me use apt get install ffmpeg. I think I already did that before. Apt get, let's not use the sudo, apt get install ffmpeg. Okay, we have ffmpeg installed. Next is to install Conda. So cd, so you can follow some of the, let me see if I can increase the view of, okay, so that it's much more clearer for you to see the instructions and running. Alright, so let's say cd, let's make dir, dir tmp, cd tmp. So wget https repo, Conda repo actually. So but I like to use so want to install Anaconda archive Anaconda 3 2021. I actually like to use this specific version though. Linux x86 64.sh. So this is going to download the Anaconda and you can see it's fast when you're working with servers like that. Downloads in seconds. So we already downloaded this, so let's say bash anaconda whatever. So let's follow the process with respect to installing anaconda. So let me just close this side, whatever. Okay, let me see if I can bring it down. Alright, let's just leave it and let's just. So some of these things are things you need to read, but you can just keep pressing enter to just until you get to the point whereby you need to type a yes, no. Alright, so we're getting close. So yes, so wait for some few minutes for Anaconda to be installed. So you need to follow through the instruction. Install Anaconda. It's getting unpacked. So we're going to follow through the installation instruction, some of the installation. So we need to create Conda first, then create Python 3.8 Conda, then do the installation of installing Engine and the likes. Then after that, we're going to verify the installation, then run, take one of their pre-trained models like the Kinetic 400, and then just run some inference on some few video for us to just take a look at what we come up with. So you specify yes, so that you want Anaconda to be initialized. So now we have Anaconda initiated. Then the next thing is source dot bash rc, so that you can now you have that base whatever installed already. So next is to now do the conda create. So we can follow through the instruction here. So we can do conda create Python 3 activate and all of those things. So let's go ahead and run it. Come on. So this conda is actually going to create OpenMMLab, and it's going to install Python. It's going to set up Python 3.8 on it. So next is to activate OpenMMLab. So activate OpenMMLab. So now we have OpenMMLab installed. So we can now do but I would love to give you we need to install PyTorch on this. So first we have it in OpenMMLab. So to install Python, you do pip3 install torch. I want to install torch 110 1 plus CUDA 113 torch vision. So this part is very, very crucial, because if you're installing CUDA 11.3, there are specific versions of torch that works with some specific version of CUDA and works with some specific version of torch vision, torch audio and the likes. So you have to specify those things accurately, as I am doing it. So pip install torch 1.10.1 CUDA 11.3 torch vision, let's say 0.11.2 plus CUDA 113, then torch audio 010 1 plus CUDA 113 f https download.pytorch.org/whl touch stable HTML. So this will install this specific types of PyTorch. But if you visit the download this URL, which is torch.stable, you basically see some of all those files that we're trying to download from here. And if you visit pytorch.org, you would see some of pytorch.org. You basically see some. So like, how did I get to know this is the command and all of all those things? You would need to look into some of where's this? So get started. So you want to set up PyTorch. So let's say stable 3.8. Then you want to specify. Now in this case, you're supposed to specify CUDA 11.02. Now this is Linux, right? We're working with Linux, so we can say CUDA. This is CUDA 11.8. Okay. CUDA 12.2, 12.6. Okay, and then you can actually look at all these builds, and this gives you the command that you're going to work with. So there are a lot of installation instructions, but I want you to check PyTorch to actually walk through that installation instruction. But over time, this has worked for me, and I'm just giving you a clue to some of these packages. So we have NVIDIA.SMI, we have our GPU in place. So next is we have OpenMM Lab. So now next is we have Conda installed, GPU installed, so on our GPU. So next is to install some of all these things. All right, so you paste that, and then all those things gets installed. So that's step one. Install engine, install Action 2. So to install Action 2, you have to git clone first. So I'll just copy. I'm just following the instruction there, but I had to skip this Conda installation of Python because of so as to avoid CUDA clashing with the specific version of Python. So if you look at let's say so if you look at CUDA version here is 12.7. So anything greater than 12.7 might not work on this platform specifically. So you just have to be. So now let's install Action. So let's install Action. So we have Action installed, then we can do cd Action, and then we can, so just follow through the instruction. So I'm just following through the guide on Action. So these are some of the ways by which you can actually learn. There are some things whereby you don't have to write them from scratch. You just need to see what somebody has done, or some of the sometimes you need to get exposed to maybe somebody did a work or did a research and you want people to reproduce the work. These are some of the guides, and that's the essence of having readmes. Or you could just do pip install. So we built from source. Another way to do is to go by pip install. So you can verify the installation. Let's do a pip install. Let's try, so that you know that these things work. But in this case, I want to do a pip 3. Sometimes you have to actually specify the type of pip, because if you do pip it might just assume you are installing into Python too. So verify the installation. To verify whether action is installed correctly, we provide some sample code to run an inference demo. So let's run an inference demo with some of their data here and see what we come up with. Just an inference. So in subsequent video, we'll dive deeper into video classification and the like, but this is just to demonstrate how video classification works and the likes, just to show you, give you an introduction to it. So this is action. So I'm gonna run this. So actually, if you go back to RunPod, you basically see that we have not really started anything. Okay, but you can see right now my container, I increased container to 200 gigabytes. So, but we've consumed 10% of it. So this container right now has consumed roughly, let's say 10%. That's like 20 gigabytes. So you could see that that's the reason why I had to increase the container size and the volume. So right now CPU, we are not really using anything because we are just installing. So GPU, we are not using anything yet. So just to verify that the installation is good and every other thing, so let's run this demo.py. Let's run this demo.py and let's see what we have. So this demo.py actually, assertion mmcv2 is used but incompatible. Please install mmcv. Okay, so we can do pip3, or for mmcv I think we can use mim. So that comes from here, mim install mim install mmcv. So that's going to install the mmcv. Running pip as root, user can be broken permission, blah blah blah. Use roots. So let's just do pip3 install mmcv. Okay, pip3 install mmcv. Why are we having issues with broken permissions? Okay, let's see if so mmcv here. Okay, let's run the code again to actually understand why we're having that Okay, so it basically says that mmcv is 2.2.0, which is used but incompatible. So we need to install mmcv greater than 2 or less than 2.2. So mim install mmcv, let's just say mmcv 2.20. Open mim. Okay. Okay. So here's what we needed to do. So we just okay, so here's what we needed to do. So since we needed to install mmcv greater than or equals to 2.00, so we had to just do pip install mmcv equals 2.0.0 rc4. So let's see, it's currently installing. Dismiss. So I will wait for it to build from source and the likes, which is currently installing. let me just introduce you to some more tricks, so I can also do apt get install screen. Yep. So screen is more or less like you need screen a lot, whereby you are trying to work with a terminal and you want to be able to enter another terminal. So like this is parent terminal, and you want to be able to create a child terminal that is running a background process, and then you want to come back to it once you are done with something, right? So basically I can actually create a screen and say, okay, this is a new screen, this conda activate open lab. Okay, conda activate not act 8 open lab. All right, so I can maybe run a Python script here and it's running, and then I do control AD and it takes me to the parent. Okay, and if I want to get back to it, I can create just say screen dash R and it takes me to the screen, and I resume back, and I can always go back and say AD, and I can also create another screen. All right, so this new screen I want to, let's say screen 2, right? I can also do control AD at the same time and I'm out back to the screen. When I do screen dash R, it shows me the different screens that are available, and I can basically say, oh, I want this particular screen. So screen dash R and in, and then it takes me to that particular screen. So I can also exit a screen, and when I do, since there's only one screen left, so once I do screen dash R, it's just going to take me to the one and only screen that is available. So, and I can do exit, and that takes me out of the screen. So when I do screen dash R, there are no screens available, so it skips me. So you might want to run some GPU codes on one screen in the background while the other ones are also running. So let's see. So let's get back once MMCV is fully installed. All right. So another thing that you could have done to actually fix this MMCV, whatever, is to look into this GitHub. Some people posted they had the same issue. So it's something about developers also. You might also want to look at what people are saying within the community or the challenges that they are having. So this was November 27, November 6. Somebody ran this and said it worked. About 4 people. So you could just take it and paste it and run it. Okay, so let's just run the demo video. So let's go ahead and run the demo video again. So if you run this code, which is a pre-trained model, we are using their image pre-trained model, ImageNet pre-trained model. So it tells also the top 5 labels with corresponding scores are arm wrestling 100%, rock scissors papers 0.9.5, -5, -14, massaging feet, stretching leg, opening bottle. So let's take a look at the video that was used for inferencing. So if you look at demo.py in let's go home. So root /mm action. Where's root? So I want to go into where the file is. Okay, we have root, this root. So this is action. So we run demo/demo.py. So demo, inside demo, so this is demo.mp4. so we can take this and download it to actually see the video. That's, which inference we just ran. So let's take a look at what demo.py looks like. So if you look at this is the video we just ran, video classification on. Let me see if I can expand it. So look at it within 10 seconds. So this is two people trying to do arm wrestling. So we're trying to like classify what were they doing, okay, what is happening. So look at what the system predicted. It says arm wrestling 100%, rock scissors paper, that minus raised to power minus 14 raised to power, so which means this is likely to happen. So you might also want to check out the demo.py, to learn more about their demo videos, which is what we just ran. Or you want to check out their demo.py, which is what we just ran. That's IPython, and how they were able to load the video using MoviePy, and how they were able to process it. So basically, this is simply introduction to video classification, and we used their pre-trained model. So that's to show that everything went well, was well installed. So you can literally prepare your own data sets by following through, depending on which kind of system you're trying to build. Is it an action recognition model? Is it a skeleton based action recognition, audio based, and some other things? Then also there is Model Zoo, which is one of the things I want to actually point your attention to. Model Zoo. Okay, yeah, this is the Model Zoo. So action recognition models. So there are about so many Model Zoos, yeah. So there's C with respect to the paper on the model, train model. So there's about PySlowFast, trained on Kinetics 400 data set. These are big, long convolution, deep convolutional models. This CKPT, that's the model reference PySlowFast. So if you scroll down, you will basically see the training and tests, how to use them, and then you'll see other types of models. You can video classification with channel separated convolutional network. So you might want to dive a little deep into some of all these things to have an understanding of what was taught. So I'm trying to see if I can get straight into where we have all the Model Zoos. Let me see if I can pick the URL from here. All right, so of course installation, and then existing hand Model Zoo, yeah. So you can run inference on existing models. So you can have your own custom. You can actually do. So what I want you to do is, I want you to play around with these different types of checkpoints, then config paths, play around with different types of configuration paths, and have your demo video, and then run this to be able to generate the results. So follow through everything I've done, and then make use of this pre-trained model to be able to do some video classification. Just play around with the Model Zoos. But let me walk you through the Model Zoo itself. Device is not clicking. Oh, okay. All right. So to check out the model zoo, action recognition model. So so there are different types of model. There's video retrieval models. There's action recognition model. There's models. Let me click on model zoo summary. Good. So in this model zoo summary, we list all the algorithms we support. You can click to jump on different models. So go over this action recognition new model, about 6 checkpoints, action centric. So there are about 35 papers implemented and about 189 checkpoints and model zoos. So Kinetic 400 action recognition pre-trained model. This is the config file. Okay, and this is the link to the model, to the readme. So you might want to check them out. So let's check out the readme. Okay, and of course you can access the checkpoints, which is the pre-trained model .pth. If you click on it, that will give you the URL of the .pth model. So literally you can actually run your own custom pre-trained model, just Python, or you rewrite your own demo.py, and then you pass in the config file, which is this, and then the pre-trained model, and then the video inference, and it's going to give you the results of what was detected in the video you passed. So it's a very simple logic or illustration. So that checkpoint I just downloaded, if I post it, this is a checkpoint URL. But it's just that you have to pay more attention to. You can see it ends with .pth. So you can actually, this is a Kinetic 400 C3 C2D model, convolution model. So you might want to check them out. You might also want to, that's the checkpoints. So this action recognition model that I've been trained on Kinetic, that's 400 classes pre-trained models. So sometimes we don't have to retrain our own model. This is UCF 101. It was trained on 101 classes, action classification. All right. This is Kinetic 700. These are Kinetic 700, the config files and corresponding link to the checkpoints trained on 700 classes. This is trained on 710 classes. Kinetic 600 trained on 600 classes. This is action detection. Okay, pre-trained models. Then this is AVA. So you might want to check out some of the links, which is URLs to some of their the papers, research, and the likes. Then we have slow fast, multi-sports. That's for football, sports, aerobics, basketball, volleyball, skeleton-based action recognition. If you want to dive into predicting actions based on skeleton. So this is simply introduction to some of all these very interesting concepts, and there are a lot of pre-trained models here. So that's the reason why I'm not going straight to how do we train our own from scratch. So if you want to train your own from scratch, it's just a matter of you just going to how you can prepare your data set, right? It's following through the instructions here, all right, and then go to training and tests, whereby it guides you on how you can train. So they have a training script whereby you just need to create your own config file and the pre-trained, and then you're able to go ahead to train your model and export the model, and then of course run inferences, which is very, very simple and straightforward. So that's that with respect to introduction to video classification. So try to play around with some of those pre-trained models and their results, and I look forward to seeing you in the next class.
Alright, congratulations for coming this far, and I'm so proud of how far you're coming. Honestly, you're doing really, really well, and I'm so proud of you. Alright, in this particular class, we just learned video classification, right? And we worked with data, and then we were able to train the model to be able to classify the different type of video. Alright, so there's going to be an assessment for you in order to test everything that you've learned in this class. Just as I have been able to run the video through the pipeline, and I was also able to prepare the data, prepare the model, and also run the inference, I want you to do the same thing on a very small sample of video that I'll be sharing with you as a test, as a take-home assessment. Alright, this is going to be shared with you via Google Classroom. I want you to run through it step by step as given to you instruction-wise. Alright, run through them step by step, and I look forward to seeing your response. I look forward to seeing your solution, and I definitely look forward to seeing you in the next class. Enjoy yourself.